We'll start our recording. So when we last left off, we discussed methods to prepare epoxides and methods to make epoxide derivatives. So we're going to review methods to make epoxide derivatives and talk about methods to prepare ethers. So we're going to talk a little bit about acid catalyzed opening of epoxides. And there are two mechanisms that can be at play. The first of which is an SN2-like mechanism. If your epoxide carbon atoms are primary or secondary, you can sometimes see nucleophilic attack at the less highly substituted site. If you only have primary or secondary carbons present, your nucleophile will preferentially add to the less hindered site. This is commonly seen if you treat an epoxide with hydrochloric acid. We protonate our epoxide, and then from there, our nucleophile attacks the least hindered position. So in this case, if we have a secondary and a primary position, which site is less hindered? Primary or secondary? What's the least hindered site for an SN2 attack? The primary site, exactly. So we attack and we open up the epoxide in an SN2 manner. However, if a tertiary carbon is present, reaction at the tertiary carbon is preferred under acidic conditions, as the tertiary carbon has the most electrophilic cationic character. So in this case, when we protonate our epoxide, we now have a tertiary carbocation. And this tertiary carbocation can readily stabilize a positive charge. As a result, attack still occurs with inversion, but what we see very clearly is that our regiochemistry now favors the Markovnikov product. Does this idea make sense to everyone for acid catalyzed epoxide opening? Okay, so let's keep going then. So let's try to predict and draw the product for this reaction and draw a mechanism for this reaction. And is there any intermediate generated over the course of the reaction? So let's take a few minutes and let's work over the next 3 to 4 minutes on drawing out a mechanism for this reaction. I'd like you to share your responses as a photo of your written work in the chat. You can explain steps in the mechanism verbally or in the chat, or you can annotate your proposed mechanism directly on the class whiteboard. I'd like you to pay special attention to the regiochemistry and stereochemistry of your product. So, does anyone have any initial proposals or thoughts for the mechanism?
Is the bromine going to attack the secondary carbon?
So, looking at our two potential sites of reactivity, we have a tertiary and a secondary position. We're treating this epoxide with hydrobromic acid, so we're working under acidic conditions. So under acidic conditions, which site is more reactive? The tertiary or secondary site under acidic conditions?
Tertiary?
Yep, exactly right.
Oh, okay.
So then, in order to activate our epoxide and prepare our epoxide for this reaction, what's the first step under acidic conditions? So we have this epoxide, it has some basic lone pairs. So what's the first step going to be? Yep, we'll protonate the epoxide. Yep. From there, that in turn generates this oxonium ion. And as we discussed, under acidic conditions, the tertiary carbon is the most reactive carbon. So we see an attack that follows Markovnikov regiochemistry. We attack the carbon that can most readily stabilize a cationic charge. So then, my question to all of you is, what face does the bromine or bromide ion attack from? If our epoxide is on the top face, where is our bromine atom installed? Should it have a dash or a wedge?
Dash.
Yep, exactly right. And the reason for that is that the bromine atom attacks from the opposite face to our epoxide, and this results in a net inversion of our carbon stereocenter. So epoxide opening occurs with anti-stereochemistry and Markovnikov regiochemistry. So this would be the single product that we observe as our major product. Does that make sense to everyone? Does this example make sense? Any questions on this example? Okay, so let's take a look at epoxide opening under basic conditions. So under basic conditions, I like to think of this as a true SN2 reaction with all of the regiochemical and stereochemical implications of running an SN2 reaction. Epoxide opening under basic conditions follows anti-Markovnikov regiochemistry and anti-stereochemistry. The nucleophile attacks at the least hindered carbon, and reaction does not occur efficiently for tertiary carbon. So for an SN2 reaction, primary is fastest, followed by secondary and tertiary. So following an SN2 mechanism, our nucleophile attacks our electrophilic carbon attached to the epoxide from the opposite face to the epoxide. We open the epoxide and make an alkoxide ion. This alkoxide ion can be protonated or intercepted with an electrophile. So in this case, we're just showing the protonation of the alkoxide ion. And that in turn generates our anti-diol or trans diol. Does this mechanism make sense to everyone? So in this case, when we have a choice between a tertiary and a secondary site, we attack the least hindered site or least hindered carbon. Does this mechanism make sense to everyone so far? Is everyone comfortable with this mechanism proposed so far? Okay, so let's keep going and let's summarize. So if we compare acidic and basic conditions, so under basic conditions, we have an SN2 process where we attack the least hindered carbon. Under acidic conditions, we follow Markovnikov selectivity in terms of regiochemistry. So we protonate our epoxide and we open by attacking the most substituted carbon. Does everyone see the distinction between acidic and basic conditions? So they have different regiochemical outcomes, same stereochemical preference for the anti-product. Okay, so when we think about base catalyzed epoxide opening, one thing to note is compared to other ethers, epoxide rings can be cleaved under basic conditions at high temperatures. The strain of your three-membered ring is relieved on ring opening. And if you use hydroxide, you can synthesize trans 1,2 diols. One thing I would like you to note is most nucleophiles can open epoxides. So this method is a wonderful way to make derivatives of alcohols. And that's why epoxides are often quite useful in synthesis. So does everyone recognize that you could just as easily, for example, take this epoxide, I'm going to draw it with stereochemistry, and you can open it with, for example, with something like sodium cyanide, right? You have just another nucleophile, which is going to open your epoxide. Just because we've changed the nucleophile doesn't mean that the mechanism has changed. The nucleophile still opens the epoxide from the opposite face via an SN2-like mechanism. So does everyone see how epoxide opening under basic conditions is a relatively general reaction? Okay, so let's try to apply what we've learned. And I'd like us to take a few moments to try to predict the products from the following reaction and draw a mechanism for the following reaction. So we're treating an epoxide with ethoxide ion. So what is going to happen and what does the arrow pushing mechanism look like for this reaction? So let's take about 3 minutes to work through this example. And ideally, I'd like a student to try and share their proposed mechanism as either a photo in the chat or even better, an annotation on the class whiteboard. You can always use the annotate tool with your mouse under the Zoom meeting options. And it would be nice so that way I can verify and get a sense of how students are drawing out their arrow pushing mechanisms for these types of reactions. So in this case, since we're treating it with ethoxide, is that a base or is it an acidic reagent? To answer the question in the chat. Are we under acidic or basic conditions? We're under basic conditions. So then, what would the mechanism be under basic conditions? Will our nucleophile attack at carbon A or B? So we have the student drawing out that our nucleophile attacks the least substituted carbon in SN2 fashion, and that opens our epoxide. Okay, so would you be able to draw the product after that addition step? Oh, perfect. We have multiple students annotating the structure of the product. That's great to see. I would double check the carbon count for that product and just make sure your final structure has the same arrangement of bonds. So if we attack carbon B, we'll generate an alcohol and an ether, right? So both of these structures need one more carbon. Does that make sense? Perfect. Perfect. Wonderful. To see students sharing their proposed responses, and these responses look reasonable. So let's draw out a mechanism just so that we have it saved as part of the instructor solution. So our nucleophile, which is ethoxide, will attack and open our epoxide at the least hindered or least substituted carbon. That in turn will give us the alkoxide derivative as well as an ether. And of course, if you decide to quench with water or H3O plus, you'll just protonate your anionic species and generate your neutral alcohol. Does this example make sense to everyone? Does everyone see how under basic conditions, we follow an SN2 mechanism? Perfect. Okay, so one nucleophile that can be used in epoxide opening that is quite useful to consider are Grignards. Grignard reagents can be used to attack ethylene oxide as well as other epoxides, and this epoxide opening occurs via an SN2 mechanism. This allows you to add this ethyl alcohol side chain to any Grignard reagent. What's important to note is that acyclic and other larger ring ethers do not react. So this is a unique reaction of epoxide. So we can open epoxides with Grignard reagents and generate substituted alcohols. Remember, this occurs via an SN2 mechanism. So it has the associated regiochemistry attacking the least hindered carbon and stereochemistry. In the SN2 reaction occurs with inversion of your stereocenter. Does this make sense to everyone so far? Does everyone see how Grignards are pretty useful reagents for forming carbon-carbon bonds? Another thing that I'd like you to note, installing an R group adjacent to an alcohol, it's a pretty interesting case of a disconnection that's known as polarity reversal, in that it allows us to form bonds between two carbon atoms that are typically very difficult to form bonds between. Notice how this bond forming reaction utilizes an irregular pattern of reactivity, right? The site and the carbon that's alpha to this alcohol functionality is typically viewed as an electronegative or relatively electron-rich carbon for most reactions. In this case, however, epoxide opening, we're using this carbon as an electrophilic carbon. So this is useful synthetically for forming bonds and generating compounds with an odd arrangement and an odd connectivity of bonded atoms. Does this idea make sense to everyone? How this is a very different pattern of reactivity than when we're looking at, for example, addition into a ketone, right? Where it follows more traditional patterns of reactivity. We have a nucleophile attacking a traditionally electrophilic site. In this case, when we go through an epoxide, this adjacent alpha carbon is electrophilic and can be attacked by nucleophiles. Ethoxide is a base because generally anionic derivatives of nucleophiles, generally most anions are at least slightly basic. And if you look at the pKa, for example, of ethoxide, if you look at the pKa of ethanol, the pKa of ethanol is like 17, so it's a relatively weak acid. So if you look at ethoxide, a weak acid, when deprotonated, generates a relatively strong base. Does that make sense? So generally, most anionic derivatives of alcohols or anionic derivatives of nucleophiles are going to be basic. So when you see an anionic derivative, in most cases, you're operating under, well, it's best not to think about it in terms of Lewis acids and Lewis bases, because when we think about acidic or basic conditions, it's referring to the nature of your nucleophile. And it's referring to whether or not the epoxide's protonated. When you're going through a protonated epoxide or like an oxonium-like intermediate, then you start to have to consider which of the carbon atoms can most readily stabilize a cationic charge. Well, when you're under basic conditions, you have a strong nucleophile, you have a relatively localized charge on your nucleophile, and then you're considering and then you're essentially looking at which site is easiest for the nucleophile to approach. So you can open epoxides under Lewis acidic conditions, but that's a little bit different in terms of what other side reactions can occur. Did that answer your question? Yes. So if you're under acidic conditions, you protonate your epoxide oxygen, and now you're looking at an oxonium-like intermediate where you're thinking which of these carbon atoms can stabilize a positive charge. And that's based on substitution. While when you're under basic conditions, your epoxide is not the best leaving group, but you can open the epoxide with a sufficiently strong nucleophile. And then it's just a formal SN2 reaction. Does that address the questions in the chat? Perfect. So let's try this out, and I'd like us to predict the products from the following reaction and draw a mechanism for the following reaction. So we treat this epoxide with a Grignard reagent. So let's take about 3 minutes and let's try to draw an arrow pushing mechanism for this reaction. So would anyone like to share their proposed arrow pushing mechanism for this reaction? So we have our nucleophilic Grignard reagent. It attacks the least substituted position and opens our epoxide. Okay, perfect. Would you be able to draw the product from that first step? Oh, let me keep it in the same view. Okay, would you be able to draw the product from that first step? And remember, the nucleophile is attacking the electrophilic carbon of the epoxide. And then remember, when we open the epoxide, the alcohol or the alkoxide ion ends up on the other carbon. So we're almost there. I would just double check the location of the alcohol. And based on your arrow pushing mechanisms, I would draw the bonds between the atoms based on your arrows and break the bonds indicated. Yep, so this structure is almost perfect, just needs one more carbon. Perfect. So this is our alkoxide ion that we've generated. And then when we treat with water, what happens? Would you be able to show that next step? So we treat with water. What is water doing? Yep, it's just protonating the alkoxide ion. Perfect. And then one more arrow. Yep, perfect. Exactly right. Wonderful. So the student response looks perfectly reasonable for this mechanism. So let's clear the responses and let's redraw the instructor solution. Okay, so we have our epoxide and our nucleophile is going to attack our epoxide at the least substituted carbon. That in turn generates an alkoxide ion. And we can trap this with electrophiles, or we can just protonate it. In this case, we're just protonating it. And that in turn gives us our desired substituted secondary alcohol. Could we make this using a Grignard? Sure. But this allows us to access relatively unique patterns of reactivity. Does that make sense to everyone? Does this mechanism make sense to everyone? Now, to ask a question that, and don't overthink this question too much, could you use Grignards for epoxide opening under acidic conditions? Are Grignards compatible with acidic conditions? No. Okay. So it's one case where if you're using a Grignard, you're only going to get one regiochemical outcome. Okay, perfect. Okay, one other thing that I want to bring up, because they do pop up in the literature, are structures known as crown ethers. These are large rings consisting of repeating, in this case, ethoxy or other fragments. They're named as X crown Y, where X is the number of atoms in the ring and Y is the number of oxygen atoms. So 18 crown 6 is an 18-membered ring with 6 oxygen atoms. Now, what these crown ethers are really good at doing is coordinating and sequestering cations. And this allows you to solvate cations, and they can activate. So crown ethers are typically used as additives to activate bases or nucleophiles. So if you have potassium T-butoxide, for example, the potassium is associated with your T-butoxide. However, if you sequester this cation, so this is our crown ether, and we sequester our cation, we now have a more reactive, essentially a more basic anion than usual. So what this means is you can very easily utilize this more basic version of T-butoxide to complete elimination reactions that would not be efficient without the added crown ether. So we can get some really difficult elimination reactions to go to completion by using a crown ether to activate our nucleophile or activate our base. Does everyone understand the potential use of crown ethers and their role in reactions? They're really good at coordinating and sequestering cations. Any other questions on this topic? Okay. What we're now going to talk about are thiols and sulfides. So thiols are sulfur analogs of alcohols. They have generally offensive odors. They're named with the suffix thiol, while an SH group is known as a mercapto group. So for example, if the thiol is named as a primary substituent, this is known as ethane thiol, cyclohexane thiol. If we're naming our mercapto group as a substituent, we would call this compound meta-mercaptobenzoic acid. Does this make sense to everyone so far? So a common name for many thiols is mercaptanes. So like methyl mercaptan is CH3SH. So as part of the iupacadoptan, mercapto is a common prefix and naming convention associated with thiol functional groups. So let's look at some examples of and rules for naming sulfides. Now, sulfides are sulfur analogs of ethers. They're named by the rules used for ethers, but you replace sulfide with the word ether and alkyl thio in place of alkoxy. So there are a few rules for naming sulfides just like ethers. Method 1, you can name each alkyl chain attached to the sulfide, and you add the sulfide suffix to the end of the name. In method 2, you name the longest chain on either side of the sulfide, and you name the sulfur alkyl thio group side chain, adding the thio suffix. If the sulfide is not attached at carbon 1, you assign the sulfide a carbon locant number, or in this case, the alkyl thio group. You place the name of the shortest side chain in front of the name with the SR suffix. So for example, using naming convention 1, we'd call this compound dimethyl sulfide. Correspondingly, if we have two different substituents, we can call this methyl phenyl sulfide. If we're naming sulfur as a substituent, and one thing I'd like you to keep in mind here is that sulfides are lower priority than alkenes, which are lower priority than alcohols. And thiols are sort of in the middle. So notice how alkyl thio groups and mercapto groups have different priority. This is a priority list that we'll talk more about, but essentially the highest priority group gets the lowest locant number preferentially. So when we have an alkene and an alkyl thio group, such as part of a sulfide, the alkyl thio group gets the lowest priority number relative to the alkene. So that's why we call this 3-methyl thio, because it is an alkyl thio group, cyclohexene. Does this idea of priority make sense to everyone? Does everyone see?
I have a question, Professor.
Please go ahead.
I have a question. Okay, so is it methyl thio because there's a sulfur attached to the methyl group?
Yes, that's correct.
Okay, thank you.
So you name the side chain attached to sulfur, in this case methyl, and then you add the thio suffix. So this entire side chain overall would be called a methyl thio side chain. Does that answer your question?
Yes, it does. Thank you.
Perfect, perfect. So let's keep working through these examples. And let's look at some examples of naming sulfides. So let's start with these first two sulfide examples. So a sulfide is not a very high priority group. And as a result, if you have a choice between a sulfide and an alkyl group in terms of preference. So in terms of preference, if you have to pick between a sulfide and alkyl group, you'll generally prefer to give the sulfide the lowest locant number. So let's try and take about 4 to 5 minutes and let's name the following two compounds. So when we talk about sulfides and alkyl groups, one example that I want us also to look at is the following that I'm drawing in. So one thing to keep in mind in terms of our priority list, we have our alcohols, we have our mercapto groups, we have our alkenes, we have our alkanes, and our alkanes, chlorides, and our ethyl thio groups are about equal in terms of priority. And the real tiebreaker comes down to alphabetical order. So keep that in mind as you work on example A and B. We already have our first proposed name for example A, which is isopropyl phenyl sulfide. What does the class think about the ordering? What should go first, isopropyl or phenyl? So when we're trying to name this compound, which alkyl group should go first alphabetically? So in terms of alphabetically, the phenyl, yes, should go first. So we'll name this as phenyl isopropyl sulfide. Yep, perfect. Any questions on this first example? Okay, so let's try to name these next two examples, keeping in mind that our alkyl thio, alkyl group, and halide substituents are about equal in terms of priority. So the key tiebreaker is based on alphabetical order and minimizing locant numbers. So would anyone like to try to name either of the two compounds for example B? Would anyone like to give an attempt at naming one of these two compounds? Let's take a few more minutes and I'd like to see some proposed names for these compounds in the chat, shared verbally or drawn out on the class whiteboard. And if there are any questions I can address as we work through these examples, Don't be shy to ask your questions in the chat or verbally.
Professor, I have a question.
Yes, please go ahead.
So like I'm confused on how to like determine the best way to like number it.
So in the event that you have multiple groups with the same priority, then the tiebreaker then is based on assigning the lowest locant number to the first substituent in alphabetical order. Does that make sense?
Yeah.
Okay.
Yeah.
Perfect.
Thank you.
So we have some proposed names for the first compound. So we have two proposed names. The first of which is 1-propyl 2-ethylthiocyclopentane. So in this case, they're adopting the following naming convention and numbering convention. The second example, or the second proposed name, would you be able to retype it? The chat was scrolling a little bit quickly. I believe the second proposed name was 1-ethylthio-2-propyl cyclopentane. Okay, so the alkyl and your thio group are pretty close in terms of priority. They're pretty close in terms of priority. So then the tiebreaker comes down to alphabetical order. And if we compare ethyl, thio, and propyl, what's first alphabetically? What's first, ethyl, thio, or propyl? The ethyl, yep. So this second name would be preferred. So to really illustrate this idea that when you're comparing thio or alkyl thio groups and alkyl groups, it comes down to alphabetical order. Let's try to apply what we've learned and let's name this second compound. Would anyone like to propose a name for this second compound, keeping in mind what we observed earlier? Would anyone have a proposed name for the second compound? So we have a proposed, we have one shared for C. Yep, so we can talk about that. We have a proposed name of 1-chloro 2-methyl 3-propyl thio cyclohexane. Okay. So chloro is first alphabetically. Yep, this proposed name looks perfectly reasonable. Looking up at this second compound that we drew out, one student noted that the full name for this compound is 1-ethyl 2-methylthio cyclopentane. Now, this is a very important example as it illustrates this idea that your tiebreaker is alphabetical order when you have substituents of the same priority with identical locant numbers. Would anyone like to comment, why is ethyl given preference in this case? Why is ethyl given preference in this case? Because it's first alphabetically. Exactly right. The same reason why chlorine is given preference in this case, because chloro is before propyl. One thing I'd like us to take a look at, really just to illustrate this point for halogens, let's try to name the following compound. Let's take a moment, let's try to name the following compound. So in the first case, our halogen was given higher priority because it's first in alphabetical order. What happens if we're looking at this new compound that we'll call compound D? How would we name compound D following these rules? So looking in this case, if we compare iodo to ethylthiol, the ethylthiol group gets priority. So this compound would be named as 1-ethylthiol, 3-iodo, cyclohexane. Okay, now remembering this sort of arrangement where the alkene is higher priority than the ethylthiol group and your halogen, let's take a moment and let's try to name this last compound, compound E. So let's take a few minutes and then let's try to propose. Halogens have about equal priority to alkyl thiol groups. As we've seen in this case, do you notice how depending on which substituents first alphabetically, we have different locant numbers? That was the goal that was what was demonstrated in examples C and D, right? Chloro is first alphabetically, so it's named with the lower locant number and named with the higher priority. In the second case, ethylthiol is first alphabetically, so in turn, it gets the lowest locant number. This commonly occurs when you have substituents that are almost identical in terms of priority. Did that answer your question? Now, in terms of our ranking of priority, alkenes are way higher priority than alkyl thiol and halogens. So then, how would we name and number the following compound? So we have multiple proposed names. The common name that I see in the chat, let me just put the numbers here, is 2-methylthiol, 3-bromo, cyclopent, 1-ene. Now, one thing to note is when we're naming alkenes, can we count starting at one part of the alkene and just neglect to count through the alkene? Or do we have to count through the alkene fully when numbering? You have to count through the alkene. So the numbering idea in terms of priority is correct. It's just the actual locant numbers need to be slightly modified. So we have a proposed name of 4-bromo, 3-methyl, cyclopent. And although you wrote it as cyclopentene, to be technically correct, it's best to include the locant number for the alkene. So this would be 4-bromo, 3-methyl, cyclopent, 1-ene. But the logic behind your locate numbers was perfectly reasonable. You just need to make sure that when you're providing and numbering alkenes, that you count through the alkene. Now, just as an odd question, yeah, that needs to be corrected. Rather than methyl, it would be methyl thio cyclopent 1-ene. Perfect. So with class responses, we are finally able to arrive at the fully correct name for this compound. Now, one thing to note, just as an odd question, why don't we count like this? Why don't we count counterclockwise? What's the problem with that? What's the main issue with that method? It would give us larger locate numbers. That's correct. Perfect, perfect. So, any questions on these naming examples? Does everyone have a better sense of priority for different groups? And does everyone get a sense of the priority for alkyl thio groups and alkenes, as well as halogens and alkyl groups? Does this idea make sense to everyone? The reason why the bromine substituent gets the higher locate number is otherwise your locate numbers overall would be larger. And our first goal is to minimize locate numbers while assigning the lowest locate number to the highest priority group. Does this make sense? Okay, so we've talked about naming alkyl thio compounds and naming sulfides. Let's try to name some thiol groups. So in terms of our general priority list, we have alcohols, which are higher priority than thiols, which are both higher priority than alkenes, which are higher priority than alkyl groups, halogens, ethers, and other alkyl thio groups as part of sulfides. So with this priority list in mind, would someone like to take a shot at naming this compound? And it may look a little bit nostalgic as we've seen this type of structure before in our chapter on naming alcohols. Would anyone like to propose a name for this compound? So the mercapto prefix is primarily used. The mercapto prefix is used if the thiol is a substituent, and it's commonly used when the thiol is not the highest priority group. So since the thiol is the highest priority group, its suffix will dominate the name. So in terms of numbering, we have the following numbering system, and the locate numbers look great, but we would name this as pent 4-ene 2-thiol, where the thiol suffix tells us that we have this SH group. Does that make sense to everyone? So the thiol suffix is a suffix that is the principal part of the name, and it tells us that this compound is a thiol, and the thiol is our highest priority group. Does that make sense to everyone? So pent 4-ene, E-N-E, 2-thiol is the full name for this compound. Now, don't entirely shelve the idea of using the mercapto prefix, because in this case, we have an alcohol and a thiol, and the alcohol is higher priority. And that's really important because that controls how we number our locate numbers, and that controls whether we name our thiol as the main substituent or whether we name it as a side chain. So let's take a few minutes, and would anyone like to propose a name for this compound? In this case, our mercapto group is best thought of as a substituent because it's lower priority. So let's take a few minutes and let's try to propose a few names for this compound.
I have a question, Professor.
Yes, please go ahead.
Can you explain again, like, what makes a substituent mercapto, please?
So you name a thiol as a mercapto group if it is part of a side chain or if it is not the highest priority substituent. The mercapto prefix is used when your thiol group, your SH group, is a substituent rather than the highest priority group.
Oh, okay. Because
So
it's in this case the OH is higher priority, right?
yes, that's correct.
Okay.
So then we name our mercapto group as a substituent.
Okay, thank you. Got it.
So we have a few proposed names in the chat. Remember, if the alcohol's the highest priority group, you don't have to name it like hydroxy. So we have a few proposed names in the chat, the first of which is 5-isopropyl, 7-mercapto, octan-2-ol. Remember, if we have an alcohol, the suffix is replaced with ol. What does everyone think of this name? Do you agree or disagree? Do we have any questions on this proposed name? So our suffix changed to ol. In terms of ordering, I have a lot of students commenting that they want mercapto first. Okay, so we name this as 7-mercapto, 5-isopropyl, octan-2-ol. Perfect. Remember, the alcohol has to be acknowledged in our suffix. The highest priority group is almost always acknowledged in the suffix. Does this example make sense to everyone? Okay, so let's look in a case now where we're naming a typical thiol where the SH group is our highest priority group. Let's take a few minutes and let's try to name this compound using the IUPAC convention. So let's take a few minutes to try to name this compound. And I'd like you to share your proposed names for this compound in the chat or verbally. And remember, in this case, our thiol group is our highest priority group. So would anyone like to share a proposed name for this compound? So we have a few proposed names, but we see a common trend. So I see a proposed name in the chat of 4-bromo, 5-tert-butyl, 7-chloro, octane, 2-thiol. Remember, thiol is part of a suffix. It's not a substituent. Does that make sense to everyone? Just like the OL suffix is related to an alcohol, the thiol suffix is related to a thiol. But other than that, the naming and ordering of the substituents looks great. Bromo before tert-butyl alphabetically, chloro next, thiol is part of the suffix. And the locant numbers look perfectly reasonable as follows. Any questions on this example? Any further questions on this example?
In the previous example, when you put the octane and we had the all as a suffix, you omitted the E.
Yes.
So
but for
why?
thiol, you don't omit the
Okay.
E. Yeah.
Okay.
And that's just the difference between thiols and alcohols. Does that answer your question?
Yes, thank you.
Okay, so let's talk a little bit about how thiols are made. Thiols are very similar to alcohols, except thiols can be prepared from alkyl halides via an SN2 displacement with a sulfur nucleophile, such as the thiolate anion. One problem is this alkyl thiol product can undergo further reaction with the alkyl halide to give a symmetrical sulfide. So that's an issue. However, it can be compensated by using thiourea as part of your synthetic sequence. So to prevent further reaction, thiourea is used as a nucleophilic equivalent of the SH anion. The important thing to note is when thiourea attacks and displaces your alkyl halide via a typical SN2 mechanism, you get an alkyl isothiourea salt, which does not and which cannot engage in further alkylation reactions. You can free up your thiol group via hydrolysis, and we'll show the mechanism for that. So I'm going to draw just this alkyl group as R. So we have our alkyl thiourea. Your equivalent of hydroxide is going to attack your electrophilic carbon. From there, you end up with the following intermediate, and a second equivalent of hydroxide will pull off our proton, and our tetrahedral intermediate will collapse. That frees up our thiolate anion, which can just be protonated. And as a byproduct, we isolate urea, which is easy to remove with water. Does this synthetic scheme make sense to everyone? And does everyone understand why going through thiourea is beneficial if we want to get monoalkylation and we want selectivity in our reaction. Any other questions on this example? Okay, so let's keep going then. So one common reaction that's often seen in biochemistry, although using slightly different reagents, is the oxidation of thiols to disulfides. This is a common test done to look at the effect of oxidation on protein structure and function. The thiol group may be necessary for a protein's function, or a disulfide bond may be very important for a protein's tertiary or quaternary structure, and thus oxidation or reduction of your disulfide bond can dramatically change your protein's overall structure and thus function. So synthetically, if we're just dealing with generic thiols, reaction of an alkyl thiol with bromine or iodine gives a disulfide. So just to showcase the mechanism for this reaction, so we have our electrophilic halide, or in this case, halogen. Your sulfur atom will attack your electrophilic halogen. From there, an equivalent of water will pull off a proton. We have a pretty activated electrophile now, and a second equivalent of thiol will approach and kick out an equivalent of chloride. From there, as one last cleanup step, water will pull off a proton. That in turn generates our desired disulfide cleanly. A range of oxidizing agents are capable of completing this reaction. Does this process make sense to everyone? Any questions? Okay, so one way to make sulfides is via alkylation of the thiolate. So thiolates are formed by the reaction of a thiol with base such as sodium hydride. From there, thiolates typically react with primary or secondary alkyl halides to give sulfides. Thiolates are really excellent nucleophiles and can react with many electrophiles. So for example, we have the following textbook SN2 reaction. So any questions on the synthesis of, the synthesis of sulfides? If not, let's keep going then. So sulfides are not the best nucleophiles. Sulfur compounds in general are more nucleophilic than their oxygen compound analogs. So as a result, we can take sulfides and react them with primary alkyl halides via an SN2 mechanism to give trialkyl sulfonium salts. These sulfonium salts are great alkylating agents, and a nucleophile can attack one of the groups bonded to the sulfur atom and displace a neutral sulfide. So for example, if you take the phenoxide anion and you treat it with trimethyl sulfide, in this case, it's best to think of this sulfide as a leaving group. So when our nucleophile attacks our electrophilic carbon, we can kick out a wonderful sulfur leaving group, and thus we get our desired ether along with dimethyl sulfide as a byproduct. Does this mechanism make sense to everyone? Does everyone see why trimethyl or trialkyl sulfonium salts are such efficient alkylating agents? Any questions on this example? Okay, so let's keep going then. Sulfides compared to ethers, sulfur is capable of accommodating an expanded octet. And sulfur, because the lone pairs are a little more nucleophilic, sulfur can also be oxidized up to yield sulfoxides and sulfones. Sulfides are easily oxidized with hydrogen peroxide to yield the sulfoxide. In this case, we can take methylphenyl sulfide and oxidize it up to methylphenyl sulfoxide. Oxidation of a sulfoxide with peroxy acid or excess hydrogen peroxide yields a sulfone. Any questions on the oxidation of sulfides? You don't need to know the mechanism, but you do need to know that these reactions exist and are useful tools to prepare sulfoxides and sulfones. A tosylate is a little bit different because it's not a sulfone because it's not dialkyl, right? In this case, it's bonded to another alcohol. Does that make sense? So it's different than the tosyl group. This substituent is known as a sulfonyl group. Does that answer your question? Perfect. So let's try to test what we've learned here. And I'd like you to predict the products of the following reaction. And I'd like you to keep in mind that you should always be paying attention to stereochemistry. A lot of these reactions are textbook SN2 reactions. So your product should have the correct stereochemistry, accounting for the fact that it's an SN2 reaction. So let's take about 3 minutes and let's try to draw out a mechanism for this reaction where we're taking a thiol and alkylating it to make a sulfide. And let's make sure the product is drawn with the correct stereochemistry. So in our first step, when we treat our relatively acidic thiol with sodium hydroxide, we're going to deprotonate our thiol to yield our thiolate anion. From there, our nucleophile will react with our electrophilic alkyl chloride via an SN2 reaction. And the SN2 reaction, as its name implies, is an SN2 inversion. So we see inversion at our carbon stereocenter as we generate our resulting sulfide. Perfect. So this student proposed mechanism looks perfectly reasonable, and it clearly hits the key point. And it clearly addresses the key point that this alkylation is an SN2 reaction, and it occurs with inversion of our electrophilic carbon stereocenter. So just to recap, hydroxide pulls off a proton that in turn generates our corresponding nucleophilic anion. From there, it attacks our electrophilic carbon and displaces our leaving group chloride. So that in turn generates our sulfide with inversion of our carbon stereocenter. We can check that because we start with an R stereocenter and we end with an S stereocenter. Perfect. Does this mechanism make sense to everyone? Any questions on this example? Okay, so we're at a good stopping point. So we'll archive today's